Okay, so we are in this book here, Generalized Linear Models with examples in R. We're in chapter 2, and we're on question 2.6. Now, in question 2.5, which was very similar, in question 2.5, we were meant to show that the expected value of beta 1 hat in simple linear regression, where we had just one predictor variable, beta 1, that its expected value, in fact, equaled the true value, beta 1. Okay, and that was a very complicated problem, or I mean, I don't know, but there was it's not intuitive how to do all of that, and largely because of all of these summations, and working with summations like this can be a little bit difficult. And in fact, when I first saw that question, I thought, oh, okay, well, the easiest way to do this is to just do it in matrix formation, or in matrix format, and show that it's true for a matrix, or in matrix multiple, or in using matrix math. But that's what we're asked to do in this question. So in the previous question, I did not do that. I went through kind of the longhand ugly notation. But we could have done the same thing here with matrix notation, which would have made it a lot simpler, and that's what we're asked to do here. So we want to show that in linear regression, now with any arbitrary number of predictor variables, that our estimate for beta hat, which is given here, okay, is an unbiased estimator of beta. So in other words, we want to show that the expected value of beta hat, this guy right here, is equal to beta, the true value of beta. Okay, so you can just see how much shorter this is than all of that. Okay, so the way we do this, so we have our expression for beta, and so I'm going to take the expectation of both sides. Okay, so expectation of beta hat is the expectation of the expression for beta hat. Okay. Now X and W, these are matrices, but they're constants. They're not variable. Okay, and so we can take them outside of the expectation operator, and then all that we're left with is the expectation of y. Okay, or not only left with that, but we're left with all of this taken outside of the expectation operator, and then we have the expectation of y. Well, what is the expectation of y? Well, it's our linear model, right? It's x beta. So now we have all of this. So we have the same formula as we had previously, but now where y is x beta. This is the expected value of beta. Okay, so now what we want to show again is that this is equal to this, but we have all of these other terms in the way. So what's up with that? Okay, so there is a property of matrices called invertibility. So if I have a generic matrix M, okay, M is said to be invertible if the inverse of M times M is equal to the identity matrix, where the identity matrix is a square matrix with ones down the diagonal and zeros everywhere else. Okay, well, so if I take this expression here, X transpose WX, this is just one matrix, right? Because I have a matrix times a matrix times a matrix, so I just get another matrix. And it turns out that this is guaranteed to be invertible. Okay, so that means that in my expression, so I can rewrite my expression putting parentheses in places where it makes all of this obvious. I have X transpose WX inverse times X transpose WX, and again, all of that then is the identity matrix, and the identity matrix times anything else is just that same thing, right? So I get identity times beta, which is just beta. And so now we've shown what we want to show, which is that the expectation of beta hat is beta. Okay.